All right. Hello, Math 141 students. In this video, we're going to be looking at the second part of section 3.6 from your book, which is looking at topics in the theory of polynomial functions. Tomorrow we'll be moving into 3.7, topics in the theory of polynomial functions 2. Okay, but we'll be talking about the first part today. The first part of 3.6 that we already covered looked at the intermediate value theorem. It looked at long division of polynomials. And I believe we also looked at the... Did we look at the remainder theorem? Oh, no, I guess we didn't. Okay, but we looked at long division of polynomials and we looked at the intermediate value theorem. What we're going to be looking at today is a shortcut way to divide polynomials, and it's called synthetic division. And depending on who you took Math 99 from, you may or may not have seen this before. I know I cover it in Math 99, and some of our other instructors do, but not all of them do. The idea with synthetic division is that under certain circumstances, we can take a shortcut to dividing polynomials. We don't actually have to follow the long division process. Specifically, we can use synthetic division when we're dividing a polynomial p of x by a quantity of the form x minus c. That's when we can use synthetic division. Okay, if we want to divide by, I don't know, 3x squared plus 15x minus 5, if we want to divide by that, we can't use synthetic division because it's not of the right form. If we want to divide by 2x squared plus 1, if we want to divide by 3x plus 84, we can't do that. We have to have just a plain solitary x, no coefficient, and then we have to have some constant. This can actually be a positive or a negative sign in between the x and the c, but we have to have just a plain x by itself and then some constant term here, and that's the only time that we can use synthetic division. And I'll give you an example of what this process looks like. Let's say we want to divide 3x cubed minus 9x squared plus 4, and we want to divide that by x minus 2. So the first thing I ask myself is, can I use synthetic division here? Well, the thing that I'm dividing by is a plain x and a constant term. So I can use synthetic division. It meets the criterion. The way that synthetic division works is you take this number here that's next to the x, which is actually negative 2, okay? And if this represents x minus c, my c value here is 2. And whatever your c value is, you put it down on your paper, and then you make a big long division bar, just like you're going to do some long division. Only the only values that we're going to be looking at are the c and the coefficients of all of the terms of the polynomial that we're dividing. Okay, that's it. We're not going to deal with the x's at all. We're not going to worry about them when we do this synthetic division, this shortcut division. What goes underneath here is the coefficients on each of your terms in your polynomial in descending order. So you want to make sure your polynomial is written in descending order. And also, just like we talked about yesterday, if any terms are missing, you need to put in a 0 placeholder, just like when you're doing long division. Okay. So I start with my cubed term. That's the first term. Its coefficient is 3. Then I move to my squared term. Its coefficient is negative 9. I don't have an x term, so it needs a little 0 placeholder. And then my constant term is a 4. Okay, 3, negative 9, 0, 4. And then synthetic division follows this process. Whatever this first number is underneath the division bar, you bring that straight down. Okay, 3. Then we take the 3 and we multiply it by this C value, the value that's outside of the division bar. So 3 times 2 is 6. Whatever that product is, it goes diagonally up above the bar. So 3 times 2 is 6, goes diagonally right here. Okay. Then we combine these two, a negative 9 and a positive 6. When we combine those together, we would get a negative 3, and it ends up below the bar. Then the process starts over again. Number below the bar, multiply by C. So negative 3 times positive 2 is negative 6. That goes diagonally up above the bar. Combine 0 and negative 6 to get negative 6. We have a number below the bar. We start the process over again. Negative 6 times 2, negative 12. Goes diagonally up above the bar. 4 and negative 12, when I combine those, negative 8. Okay, and when we get to the end, we stop. And then the question is, what in the heck do these things represent, right? This, believe it or not, is our answer. It's just, what does it mean? How do we write that as the answer to this division problem? Well, it turns out that this final term below the horizontal bar right here, that's always your remainder. This is your constant term, and then everything else proceeds to the left in ascending order, right? So if we have remainder, constant term, this is the coefficient associated with the x. This is the coefficient associated with the x squared. If there was another one over here, that would be paired with the x cubed, x to the 4th, and so on. Okay, so what this is actually representing here is 3x squared minus 3x minus 6, and then just like with long division, we take our remainder, negative 8, and put it over our divisor, x minus 2. Okay, so there would be the final form of the solution for that synthetic division problem. Okay. Let's take a look at the remainder theorem. What the remainder theorem says is that if a polynomial p of x is divided by x minus k, the remainder is equal to p of k. If a polynomial p of x is divided by x minus k, the remainder, whatever remainder we get when we do that division, is equal to if we took this value of k and plugged it in for the x in the polynomial. So here's an example of how you might see that applied in the book. Let's say we wanted to use synthetic division to find p of k. It gives you that the k value is 2 and that your polynomial function is 2 times x cubed minus 3x squared minus 5x plus 4. Well, according to our remainder theorem, if we want to find p of k, that's equivalent to dividing the polynomial by x minus k and finding the remainder. Whatever that remainder is, that's going to be equal to p of k. So if I take my polynomial and I divide by this value, synthetic divide by x minus 2, that's going to give me the remainder that I need to find out what P of k would be. So same thing here, since I'm dividing by something of the form x minus c, I can simply use synthetic division. I don't have to long divide. Certainly you could long divide and find the remainder that way, but you can synthetically divide as well. So I want to put my 2 value over here, put my division bar, and then put my coefficients in the proper order. Okay, and if there are any 0 terms, I want to put a placeholder there. So 2x cubed minus 3x squared minus 5x plus 4. I don't need any zeros in this case. And then we're going to do our synthetic division process. First number comes straight down below the bar, 2. Once a number ends up below the bar, multiply it by that c value that's up here to get, in this case, positive 4, and that goes diagonally up above the bar. Negative 3 and a 4 gives us positive 1. Number ends up below the bar, multiply by 2, put the answer diagonally up. Combine those, negative 5, positive 2 is negative 3. Multiply by the c to get negative 6, put it up. Combine there, negative 2. There's our remainder. Okay, so if a polynomial is divided by x minus k, the remainder is equal to P of k. So this is telling us that P of k, if we plug in the number 2 to this polynomial, that's going to equal our remainder, negative 2. There'll be a few problems on the homework that are like this. Whether you think this is faster or whether it's just faster to plug in the number 2 to all of your x values, you know, it's basically 6 of one, half a dozen of the other. You can evaluate that function either way. The book did ask us to use synthetic division. If it hadn't asked us that, if it had just said find P of k and given us the k value, we also could have just plugged the 2 in for each of the x's and evaluated it that way. But it specifically asked us to use synthetic division. And that's the remainder theorem. Let's see. Last thing that really comes up in this section, the last theorem, is the factor theorem. And then we'll take a look at a few more examples of problems like you'll see from this section on the homework assignment. Okay, but first we'll discuss the factor theorem. The factor theorem says a polynomial P of x has a factor x minus k if and only if P of k is equal to 0. Okay, a polynomial has a factor x minus k if and only if P of k is equal to 0. So if we plug our k value into our polynomial and that equals 0 when we plug it in, then x minus k is a factor. This is something that we actually know from doing quadratics, right? If I have, x plus 2 and x minus 1 equals 0, right? That would be a factored form of a quadratic equation, and each of these guys is called a factor. Okay. And each of these, a negative 2 and a positive 1, if I plugged either of those into the original quadratic here, which would be an x squared plus x minus 1 equals 0, if I plug either of these in here for the x's, negative 2 to both x's or positive 1 to both x's, it's going to give me 0. Okay, so plugging in these values gives me 0 in the function, which means that x minus those values would turn out to be the factors. Okay, and that's what the factor theorem says. So, a couple of things that we can do with the factor theorem. Here's an example from the book. It says to use synthetic division to determine whether the given number is a zero of the polynomial. Okay, so in order to be a zero, we would need for the value of the polynomial when we plug in this number, we would need it to come out to 0. Okay, and the number that they're asking us to test is the value of -1. And the polynomial that we're given is x squared plus 4x minus 5. This is actually number 46 in your book on page 223. So we're supposed to use synthetic division to determine if this is a 0. So here's our synthetic division. This is the number we're checking, so we put it out front. We put our coefficients of our polynomial here, so 1, 4, -5. I don't need any 0 placeholders. 1 comes straight down, ends up below the bar, gets multiplied by -1, answer goes diagonally up. Combine to get 3. 3 is below the bar, multiply by -1, diagonally up, -3. Combine, -8. Because this value, this -8, is not equal to 0, because of the remainder theorem, that implies that -1 is not a 0. Okay, so no, -1 is not a 0. We could also test that just by plugging in -1. Book did ask us to use synthetic division, but we can double check our work this way. If I put in -1, I'm going to get -1 squared is 1, plus 4 times -1 is -4, minus 5. That's definitely not equal to 0. 1 minus 4 is -3, minus 5 is -8, which we can see there, -8, see? Not equal to 0. Therefore, this is not a 0 of the polynomial function. Okay. So that's one of the types of problems that you'll see in the book. Here is another type of problem that you'll see in the book. Actually, you'll see quite a few of these. This is number 66 on page 224. And what this one says is use the given 0 to find all others analytically. So they give us a 0 of, they give us a polynomial function. P of x is equal to x cubed minus 7x squared plus 13x minus 3. And the 0 that they give us is 3. Okay. So by the factor theorem, if we know that 3 is a 0 of this function, it means that x minus 3 has to be a factor. Okay, because notice if we plug 3 in there, 3 minus 3 is 0. Okay, so that's got to be a factor of this function. So what we would like to know is if one of these factors is this, what are the other factors so that I can find out what the other zeros are? Okay, so in other words, I want to be able to fully factor this. Well, this is a cubic, so I can't factor it directly like we do with some of our quadratics. So what I need to know is if x minus 3 times this stuff equals this original thing, what is this stuff? And one way I can do that is by dividing. And I can use synthetic division here. I can put my 3 out front, put in my coefficients, 1x cubed minus 7x squared plus, 13x minus 3. And do my synthetic division process. Notice that also proves that 3 is a 0, because I do indeed get a remainder of 0 when I do synthetic division there. And it also tells me, because of these coefficients, if this is my remainder, this is my constant term, my x, and my x squared, I now know that what goes in here is x squared minus 4x plus 1. So now, to find all the other zeros analytically, I would need to know what the zeros of this quadratic are. And if this factored, I could go ahead and factor it and find the zeros that way. Notice that this does not factor, so I'm going to have to use the quadratic formula to find the other zeros. And we had an x squared minus 4x plus 1. I want to know where's that equal to 0. A, B, C, and plug them into their appropriate places in the quadratic formula. Okay, plugging everything in there. So opposite of b is going to give me positive 4, plus or minus square root of b squared is 16, minus 4 times a times c would just be a minus 4 over 2. 16 minus 4 is 12. So 4 plus or minus root 12 over 2. The book does simplify these as much as possible. So it'll have 4 plus or minus. If we split up that root 12 into a root 4 root 3, we can see that that simplifies to 2 root 3. And the book will keep going. It'll split that apart into 2 terms and simplify those as much as possible to get a 2 plus or minus root 3. So all 3 of our zeros, they gave us the 1 that was x is equal to 3. Here's the other 2, 2 plus or minus the square root of 3. Because it was a cubic function to begin with, its highest power was a cube, there can be a maximum of 3 solutions, and we found all 3. Okay. Let's look at one more example, and that'll do it for this section. This is number 80 on page, I think it's 224. And it says to factor p of x into linear factors given that k is a 0 of p. Okay. Factor p of x into linear factors given that k is a 0 of p. So the polynomial that they give us is p of x is equal to x cubed plus x squared minus 21x minus 45. And the k value that's provided is negative 3. So here's what we know. If this guy is a 0 of p, it means that one of our factors has to be x plus 3. Right? Because when we plug a negative 3 in here, negative 3 plus 3 would be 0. So there's one of our factors, and then we've got to have other stuff. So we need to find the stuff, and that's where the synthetic division comes in. So we put our k value out front, plug in our coefficients, 1, 1, negative 21, negative 45. Do our synthetic division. And notice again, when we do our synthetic division, we get a 0 remainder here. We should get a 0 remainder because this is a 0 of p. It should divide evenly into it. There shouldn't be a remainder left over. Okay. And what that tells us is that when we pull out this factor of x plus 3, what's left over, this stuff, is an x squared minus 2x minus 15. Okay, and we're trying to factor as completely as we can. So we factored out the x plus 3. Then since this is quadratic, we look to see, can that be factored anymore? And as it turns out, yes it can. So this x plus 3 hangs out. Here, to get an x squared, I need an x and an x. And then the only two integer combinations that'll get me to multiply to a negative 15 are a 1 and a 15 or a 5 and a 3. Since I need to make it to a negative 2x in the middle, probably not the 1 and the 15, probably going to be the 5 and the 3. And since it needs to be a negative 2, I have to have a minus 5 and a plus 3. Certainly you could leave it here. This is a completely acceptable answer, but the book does note that since you have a repeated factor of x plus 3, the book will write the answer as x plus 3 quantity squared times x minus 5. And there it is in fully factored form. We can't factor it any more than that. Okay. So that's what you'll see in the second part of 3.6. Take a look at the homework problems, and if you have any questions, feel free to bring them up in class. Thanks for watching.